Well, Graham, thanks so much for the invitation and the opportunity to speak about an area that's really, always something that we're striving as a species to do, which is to further our extent in exploration. And it's not to conquer, because you certainly can't conquer nature, but you can learn to adapt to it. And we've got some real challenges. The reason I still do the teaching, even though I'm retired, is because I look at my role as to pass the torch to the next generation. And I had great mentors throughout my career, and now this is my opportunity to pay it back. So I think that there was a number of different topics that I offered that I could do, and you all wanted getting humans to Mars. So we'll start with that. I was a Navy flight surgeon. I'm a neurologist. I was a Navy diver, a Special Forces parachutist, a naval flight officer, bombardier navigator, and at NASA I got transferred there because my wife was an astronaut, and that's really how I got there. It wasn't because of my skill sets. But anyway, I spent 8 years there. Oops, I better turn my power on. I spent 8 years at NASA, 4 as a military officer and 4 as a civil servant. But since then, I've mostly doing stuff on the commercial side of things. Before I left NASA, I was on after the Columbia mishap, they created a investigation board called the Spacecraft Investigation Team. That was in the aftermath of the Columbia accident board. And that went on for 4 years, and we wrote 3 different publications, the last of which was basically how the crew perished and what we could learn from it. I was also a member of the Constellation, which was the program that George W. Bush put together to go back to the moon. And most of that focus was spacesuits, the EVA part of it. There was a commercial company called Excalibur Almaz that took the Russian Almaz system. That was active for a while and now has been dormant. And I was the medical director for 2 of the stratospheric freefall programs, the Red Bull Stratus and Stratic Space Dive. My Mars project was called Inspiration Mars, that was funded by Dennis Tito, and that there was a whole lot of lessons learned from that. It was heavily involved with NASA early on, and if any of you want information on that, it was a Mars flyby mission. I currently consult with Virgin Galactic and SpaceX and a stratospheric balloon program called Space Perspectives. And we just recently finished a 60-day head-down tilt study with 2 campaigns, and I think we had 24 subjects, which was a very extensive project, and there'll be a lot of data coming out of that. So most of my stuff now is in the academic and commercial side. So this slide I added, I didn't send this to you earlier, Graham, because I just put it together. I kind of wanted to show the commonalities between wilderness medicine and a human Mars mission. And for those of you who've spent time in the outdoors, you can certainly attest to the fact that you're out really far, you don't have cell coverage, you don't have any way of getting a hold of anybody. You can feel the plight you get if something goes awry. And even something as simple as a sprained ankle where somebody can't ambulate anymore can be a huge problem. So you have the resource constraints in any system, including a healthcare system, includes 4 different areas: personnel, equipment, procedures, and training. And that's something I actually do a talk on the space medicine applications and how we use those 4 components together. Comm constraints, comm always sucks no matter what. And it's really sucky when you go far away. You also have time constraints that you've got to beat a weather system. You've got to beat something that's impending, running out of consumables like oxygen or food or water. All those things that are commonalities between the wilderness activities and deep space activities. And the key thing there is, as a master's of public health, one of the things I always say is it's better to prevent a problem than to try to deal with the consequence. You should be prepared for the consequence, but in general, a good risk management can help significantly. And Wilderness Medicine Society has a big program now on risk management. So where can we go in the universe? And this is kind of a simplistic slide. Right now, we've had 12 people walk on the moon, and we've had 18 that went to lunar orbit. And that's in just rough generic things, it's 250,000 miles to the moon. And so that's going to be our next target. And people always say, well, you can't, why waste time going to the moon? And let's just go to Mars directly. And there's proponents of that. But the way I look at it is, anybody who's done real expeditions knows you have to have a base camp. You don't go to the summit of Everest without going to base camp. And part of it is to pre-position and closer proximity to the final destination. You can have you have backup that's closer by. And so I look at it simplistically, and to go to Mars, you use the moon as base camp. And there are many reasons why. It's a lot less energy to take, to take supplies from the moon to Mars than it is to go from the Earth to Mars. And just to give you a simple perspective, we call it delta V, the change in velocity that it takes to get something from Earth to low Earth orbit is about 18,000 miles per hour of velocity. To go to the moon, it's 25,000 miles. And to go to Mars from the Earth is 35,000 miles an hour. So that's the delta V. So it only takes 10,000 miles an hour to go from the moon to Mars. So, and there are other things out there too. There are libration points, which are gravity wells between the sun and the sun and the moon, the sun and the Earth, and between the sun and Mars. So those are the libration points, are where you could put something in that will station keep on its own. It's kind of like a eddy current in a deep ocean system. Mars is interesting because we can see it with the naked eye. In fact, it's close right now. And if you look up at the eastern sky, you can see this kind of reddish looking star, and that's Mars. And if you have any, even a binoculars, you can see different aspects of it. And certainly with telescopes, even small telescopes you can buy in the store. It's got seasons, it's got weather, it's got terrestrial terrain features that are really interesting. It probably has life there at some point because there's been such vast water features on Mars, and it's close enough that we could settle. We'll talk a little bit about some of the differences. These are just some of the, obviously there's been a number of movies that have been made about Mars. Some of them have stretched the science part, but you can see that Mars is always something, it's our red neighbor, and everybody looks up to the sky and says, hey, we could go there. Now, Mars compared to the moon is in the 30 to 40 million miles away. So it's quite a significant difference. 250,000 miles versus 35, 40 million miles is a long way. And then we'll talk about some of the consequences of that. These are some of the features that have been seen by the Mars Reconnaissance Orbiter and other observation systems, and their hearts. Isn't that cool? I mean, who could imagine that a heart-shaped structure could be formed? This has intrigued a lot of folks. Can you see my little arrow around that middle object? And in the middle of that, you can see a face. It looks like a face. There's just no question about it. It looks like a little face. And then this one looks like a smiley face. So nature, unless maybe somebody's out there actually sculpting things, and there's even monoliths on certain structures that are probably rock formations. So to go to Mars, we have several different factors that we'll talk about. One is, what are you going to do there? Are you going to just go and do a flyby mission? The Inspiration Mars mission, a lot of people poo-pooed it, but it was about 40 times cheaper than a surface mission. And the reason for that is that it was a lot less complicated. It was based on the idea that Apollo 8, which in 1968 orbited the moon and then came back. And that tested out the systems. Can you get there and can you get back? Can you survive the Earth reentry, which is because you have a higher delta V, you're going to have a lot higher thermal energy. Are you going to stay for a certain period of time? And basically, the three general stay missions are a sortie, a outpost, and a settlement. And for a sortie, the space shuttle did sorties. It went up and it came back down. One space station, which I'm wearing an Expedition 1 shirt. I don't know if you can see this, but that's Bill Shepard's mission, which was the first expedition launched, or it became human-tended in 2000. So we're just now on the 20-year anniversary of an outpost, continuously manned since 2020. And then the ideal, mission would be one where you could go for extended periods of time, mine. You could do science missions. There's any number of different things you could do. And there's even there's a group called Mars One, which is a one-way mission. So people that go there, and I'm not saying you'd send your your mother-in-law there, but there were quite a few people that have paid money to just get in the queue to do a Mars One mission. So anyway, the next big challenge you have is the transit via chemical rockets, which are currently the mainstream. Thermonuclear are probably a good idea because at some point, it's a relatively sustainable system. And there are even ion plasma engines. All of this, the faster you can go, the sooner you can get out of the deep space radiation and at least be on a terrestrial surface where you can use some kind of shielding, such as the material on the surface. We'll talk a little bit about orbital mechanics because there are things that can enhance the shorten the transit time using orbital mechanics. The solar cycle has various factors. Every 11 years we have solar min and solar max, and during solar max we have higher amounts of solar activity, which are sunspots and coronal mass ejections, and those are big balls of solar energy that can cause huge problems that get if you encounter those. How big a crew do you have? What's the makeup of that? And then all the equipment constraints. We'll go into a little more detail, but the top three are the mass, power, volume. And do you use a system to provide some transient gravity en route so you're not degraded by microgravity? And the lunar surface is 1/6 G. We don't know if that's going to be protective against some of the degrading effects. Mars is about 1/3 G. And so the idea would be that if you could get 1/3 G in transit, you would be better adapted once you got to the Martian surface to tolerate that gravity, as opposed to a long transit with zero gravity. So we'll look about orbital mechanics, and these are the two major categories. They're called opposition and conjunction class. Opposition class missions, you launch from the Earth when Mars is opposite the sun. So essentially, opposition means that the Earth is on one side of the sun and Mars is on the other side. And for optimal conjunction or opposition class missions, the transit times are on the order of 300+ days, so just shy of a year. And you could stay for 40 days. But the good news is that the whole mission length is less than, it's anywhere from 600 to 700 days. A conjunction class mission means that you launch with a direct view or direct link to Mars. So what would be an advantage here is that if you had elements of human elements already on Mars, you could directly communicate with them. There are periods, if you look at this opposition class, where you cannot communicate to Mars, even if you wanted to, because the sun is in the way, and it's essentially a big electromagnetic emitter, so it's going to block the energy from radio transmission. So there are actually some periods of time during opposition where Mars and the Earth are on opposite sides of the sun, where you have no communications ability. Not just a long comm delay, you have no communications ability. So that's just a general overview of the differences in these two kinds of missions. The thing is, these are based on the rotations of the Earth and Mars, and the Earth rotates around the sun 365 days a year, and Mars rotates around the sun, because it's farther out, at almost just shy of twice as long. So its mission are in the high 600-day mission of solar rotation. So a Mars year is about twice as long, or just a little bit less than twice as long as a Earth year. And this is a breakout of it. You can look at this, what the gravity composition, the atmospheric pressure, gas composition, temperatures, all of these things are extremes. And I'll say, one thing I always like to try to talk about is what are the drivers for life? What is going to kill you the fastest? And anybody have a guess what parameter would kill you the fastest?
Lack of water.
No. How long can you live without water?
2 days.
2 or 3 days. How long can you live without pressure?
Oh, pressure and air, I suppose, would kill you.
Yeah.
faster.
So there's the pressure and there's the gas composition. So I do a lot of, and we're fixing to do a research project on this. But if you take away pressure, what happens is your blood boils and freezes at the same time, above 120,000.
So cool.
I got a video of it. I could share with y'all, but you know,
Okay.
I'll probably put it on it. But what happens is at 63,000 feet, that's the Armstrong line, and water boils. It sublimates, so it turns from a liquid to a gas spontaneously. But about 115, 120,000 feet, it reaches the physical chemical principle of the triple point, where it exists in all three states of matter simultaneously. And it's the most bizarre thing you've ever seen, because it boils and freezes at the same time. And we would put a tub of water in a vacuum chamber, take it to 120,000 feet, and then we'd make space ice. So the thing that will kill you the fastest is the absence of pressure. And there are actually humans that have survived 63,000 feet, 70,000 feet for a minute or two. But in general, if you're above the triple point line, it's going to kill you really fast. Lack of oxygen, so the composition, you can go into a 1 atmosphere room that's full of nitrogen and you will go out just like that. So oxygen is the next thing that kills you. Absence of good thermal stability. If you're out in a cold, really cold place, you won't last more than a couple of hours. So water is in the category of days, and obviously food is in the category of months. So the first thing that'll kill you is pressure, or the first thing that'll kill you by its lack is pressure. The next is lack of oxygen. The next is lack of thermal protection. The next is lack of water, and the next final is lack of food. So that's just a quick summary of what are the things that you absolutely have to sustain life. I'm sure if you all have any interest in space, you will follow Elon Musk's travails, and he's a guy that really gets things done. He's a quirky guy. He's kind of savant-like, but he has single-handedly broken the code to this, and that is heavy lift with LOX kerosene engines or LOX methane engines, and lifted heavy payloads. And this was a couple of years ago. He put 3 of his Falcon 9 boosters together. Here you can see this stack, and this was called the BFR, the Big Falcon Rocket, or the Big Frickin' Rocket, that he launched from the same complex that launched the Apollo missions. And amazingly, he brought back the 2 boosters. The third one, which was the center one, they couldn't recover it, but they could have if they had prepared, enough resources. But they would have to do it on a ship out to sea. One of his drone ships that recovers the vehicles. But to do propulsive landing, one is it cuts costs because you can reuse these things. And I think he's launched several of them, 6 times. And Jeff Bezos at Blue Origin also has propulsive landing systems, but his have only gone to they've gone to suborbital. So he goes up to 100 kilometers and brings it back down. And to go to orbit and bring one of these down is a lot more thermal energy. So even though both of them have developed propulsive landing systems, the SpaceX system has brought back from orbital launches. So this is a big factor. So it cuts costs, but why do these guys both want to do propulsive landings? Well, the reason is you cannot land on Mars in the conventional way that we land on Earth, which is aerodynamic decelerators, i.e. parachutes, various forms of parachutes. And some you can use inflatable systems, or you can use ring sail parachutes, but parachutes don't work well on Mars unless they're really small objects. Like the rovers they've launched early on used parachutes and airbags to soften the blow. But the bigger ones, the ones that the latest Mars rover that's really big, like the size of say a SUV, they have to use a propulsive system to slow it down. The atmosphere on Mars is so thin, it's enough to cause friction, but it's not enough to cause aerodynamic deceleration. So you cannot land on Mars with the size of vehicles that you need without propulsive landing. So both Bezos and Musk have realized that they needed propulsive landing. One is it saves costs for orbital launches, but 2 is it's absolutely required to land on Mars. You have to use propulsive systems like this to land large mass payloads. And of course, the Big Falcon rocket in 2018 launched one of his old Teslas, and the Starman spacesuit. This was a real spacesuit, and I was fortunate to be on the medical monitoring group that did the first human vacuum chamber test with I wasn't in the suit, but I was the medical monitor for the first time SpaceX put a human in a vacuum chamber, because there was obviously concerns there. But this is a super nifty suit. But this vehicle and Starman are on their way to the outer galaxies. I can't remember where they are now, but they're I think they're certainly past Mars and some of the middle ring planets. So Elon Musk's big effort now is to continue his dream for Mars, a Mars colony. And this is a picture. This was one of the earlier prototypes. This is that Mars suit right down here. And these things look like little kid rockets that we had in the 50s. But he's flown these things multiple times. He's blown quite a few of them up. He's up to serial number 8, which just launched on the 9th of December down in Boca Chica, which is the southern tip of Texas, south of Padre Island. And everybody, and there's not a very big community there, but everybody in that town gets evacuated during one of these rocket tests. So this is what happened. This was the serial number 8 Starship that was going up into the 30,000-40,000 foot range, and it had a fine ascent trajectory. It only had 3 of the Raptor engine, or 3 of the Falcon engines in it. But on the way down, it had a stutter of its propulsive landing, just enough to hit a little hard, rupture a tank, and then kaboom. So so serial number 8 was, destroyed in this spectacular fireball just 2 weeks ago. I don't know if any of you all watched that. It was pretty cool. So early concepts that Elon Musk had for landing on the Martian surface was to use propulsive landing on the capsule. And this propulsive landing system are the Super Draco thrusters that are used on the Crew Dragon. And they're used for the abort motor, which is pretty cool. So he always uses multiple, he always does something that has multiple uses. So these Super Draco rocket engines on the Crew Dragon are used for an escape system if you have a launch aboard, but they were also originally designed to land on the Martian surface. But what he realized is this is not enough to sustain a human, and so they've gone with these monster big rockets that are going to do propulsive landing. Hence, that's why they were testing this bigger thing. So this early on, this was the Mars landing system, but now it's evolved over time. And so this is one of the prototypes. It's changing all the time. Every year or two, they've redesigned its size and other structural features. But essentially, there are going to be two kinds of vehicles. There's going to be a tanker version that's going to go and carry primarily fuel and also perhaps consumables. And then there's the human system, which is the ship. So there are these two systems, and you can see these are monster big. You know, the crew system is 150 metric tons, and the tanker system is 90 metric tons. And they have bigger ones that can. This is the payload they can take to low Earth orbit, which is substantial. By a, it's on the same order as the Saturn V. And so this is just one of the renditions that he's had, where basically you're going to launch a tanker into low Earth orbit to refuel once the vehicle gets to low Earth orbit with the crew. And then you're going to have one in Mars orbit where you can refuel it for the way back. And then you're going to have ones that land on Mars and start to recycle Mars, certain Mars components into materials that could be used to make the LOX methane fuel for the ascent. Well, why do you need to refuel in low Earth orbit? Well, the reason is it takes 17,500 miles an hour to get to low Earth orbit. So if you look at the whole 35,000 miles per hour to get to Mars, you've used half of it up just to get a couple hundred miles off the Earth's surface. So that's why you want to refuel up in low Earth orbit, because you don't want to waste the energy lifting all the fuel you're going to take to Mars, because when you can refuel it at waypoints along the way. Now, he doesn't plan on using a Mars or a moon refueling station, but the fact is that you've got to refuel it along the way so you don't have to carry everything from the surface of the Earth. And so that's just a general concept. You want to replenish along the way. You don't want to take everything with you, because your lift vehicle would have to be just monstrously big. So, and this was based on a talk he gave in Guadalajara in 2016 and 2017 in Adelaide, Australia, about, he really wants to have a multi-planetary species. You'd land these tanker systems on the Martian surface, and their job is to replenish their fuel supply by using rovers that go out and acquire resources, which including carbon dioxide, which you can convert to oxygen, and the carbon you can use to create methane. And this is just an artist rendition of how this base is going to go. You've got a system that lands there and starts to build fuel. Then you've got systems that build landing pads, and in proximity to this reclamation fuel and oxidizer reclamation station. And then eventually you build more and more infrastructure in colonies that grow like this. So it's a very ambitious process. The thing is, it's the only way you can do this is you've got to be able to use resources that are there, whether it's water, ice, whether it's the carbon dioxide in the water, or some of the material in the actual Martian surface has high nitrogen compounds, so you can use that for fueling, for certain kinds of fuel. So you've got to use, and you've got to figure out chemical ways to transfer components on the Martian surface into useful items for your missions. So some of the challenges that we faced, just like we do on a ocean racing or ocean exploration or polar exploration, we face some of the challenges that are similar, such as the comm delays, the replenishment issue. Do you have to take everything with you, or can you pre-position stores in other places? But the things that are very different than any other terrestrial analog environment is this absence of the magnetic fields that protect us from a lot of the solar radiation. And that will, in general, increase. So as a general rule, going from the surface of the Earth to low Earth orbit, you have about 10 times more radiation than you in low Earth orbit than you do on the surface. And when you go to the moon, you've got another 5 times more than you do in low Earth orbit. And then when you go to Mars, now you're talking about 100 times more than you get on the Earth's surface. And so that radiation effect on people is one of the top concerns, because like the astronauts say, it's the gift that keeps on giving. So a lot of the effort that's going on now is to try to understand these effects of radiation in deep space, and can you use the Martian surface material tunneling in or whatever to reduce some of your radiation exposure. This is a one that is very, very dependent on distance, and that's the speed of light that radio waves travel at. And depending on whether you're in a conjunction state where Earth and Mars are on the same side of the sun, or whether you're in opposition on opposite sides, that distance changes. And as a result, the comm delay changes. But even at as close as they can be, 35 million miles away on its close point, that's still 8 minutes of comm delay. And believe it or not, 8 minutes means you no longer have the ability to have near real-time communication. And by that, I mean, going to the moon, it's maybe 3 seconds, and it's hard to do stuff. But over a couple of minutes, in the studies that have been done in training scenarios, it means basically you have to do store and forward, where you write down your problem, you send it off, and then at some period of time, somebody else answers it back. It's not like a phone call, it's more like a text or an email. Imagine what it would be like where you are trained in something and then you do not maintain a sufficient state of proficiency in it. And medicine is a prime example of that, where you're on a long transit somewhere. On the short end of things, it might be 6 months for a conjunction class mission. The transit times to and from Mars are only 6 months, but for an opposition class, it might be 180 days. So I mean, it might be 300 or 400 days. So that's time that's spent not doing what you wanted to do on Mars, whether it's to explore or to mine or to do various other things. It's just spent getting somewhere. So proficiency and training is a huge issue in medicine. How do we keep that up? You have to pre-position stuff, and if you have a problem that develops and somebody has a life-threatening emergency, you cannot turn around and come home. Just like in Apollo 13, their abort option was to abort to to lunar or to do a lunar flyby and then come back around. That was the only way they could do it. They didn't have the propellant to just stop and come back to Earth because they already had an outbound delta V. So basically the way to do that is you're going to have to abort to Mars and then come back at the earliest. You cannot just turn around and come home because of the velocities involved. That's why you want to have stuff prepositioned there. Now, this was taken from, I can't remember which lunar rover. It might be Curiosity, but this is the solar glow. This is the Martian surface, and that's Earth. Look at that little dot. It's not even a pale blue dot. It's a barely visible, scratch of a pencil. It's not like when you hold your thumb out at arm's length, that's a couple of degrees. That's what the size of the moon is from Earth. This is not a couple of degrees. You can't look home and see what the Earth is. Even from, like on the moon, you could at least see that it's blue. You could see weather systems. That pale blue dot is a very foreboding sign, just psychologically. Our top threats, we kind of outline them, radiation. We have deep space radiation from solar particle and cosmic rays. I'll briefly talk about that, but not much. We have a diminished gravity. At the very best we'll get on the Martian surface is about 0.38 G, which is, is certainly less than normal. We have the requirement to live in an enclosed pressurized system that provides atmosphere and gas composition that's compatible with life. The isolation confinement, the fact that we don't have real-time communications, we'll have bandwidth issues even at best. And that distance means that you can't get replenished or you can't do a mission for an abort. So those are some of the top things. Isn't that cool though? That's an actual picture of Earth taken from the Martian surface. Well, what do we know about humans in space and microgravity anyway is, and I update this every year, so I'm getting ready to be updated in a couple of days, or next year, which is only a week away. So we have about 150 crew years as of last January, and that's probably in the 170 crew years now. Most of it, or at least half of it, is in the hands of the Russians because they've been doing long duration missions much longer than we have. Just barely over 500 plus people have flown in orbit. More people have flown in space because they only, the ones that did an up and down. Virgin Galactic's flown several missions that classified as space, we had Mercury Redstone, which was a suborbital mission. So we've had other people that have flown in space but have not flown in orbit. One guy who's a really neat guy, Valerie Polyakov, is a Russian physician and flew one on the Mir mission. He flew 14 months, single mission. And then he flew another mission that was pretty lengthy, and he had a total day accumulation of 600 days. We've had a couple of people that have flown over 1 year mission, and I don't count. Scott Kelly says it was a 1 year mission, but it was 340 days. It wasn't a year. The Russians who flew, there are 4 Russians that flew in space over a year, 365 days. Valery Polyakov flew he flew 14 months, but all the other Russians flew 366 days. They just wanted the record and they wanted to come back. Why? Because it sucks. It's really hard to do that. The record holder is Gennady Padalka, who was one of the early ISS guys. He's flown almost 900 days in space. And we have 3 people, Russians as well, who've flown over 800 days. That is that's a conjunction class mission right there, or close to a conjunction class. So these are the cumulative totals for those over. So we have 21 people over 500 days, 10 over 600, and 3 over 800. So that gives you perspective. We could do a conjunction class or an opposition class mission based on our microgravity experience. Now, this is a picture of Mir space station. Mir means peace in Russian, and it flew for, gosh, I don't know, 13 years or so. And towards the end of its occupancy, it had lots of problems. This is one of the products we developed in the survival investigation team, which was to compile lessons learned from all of the bad things that have happened in space. And this is the link down here. If you click on it, it will pull it up. And if you click on each box, it will talk about it. The reds are loss of crew. The yellow or the oranges are crew injury, loss of mission objectives. And the yellows are events that had mission impact, but not mission, altering effects. What you can see here is throughout every phase of flight, from launch and ascent, on orbit, entry, descent, and landing, we've had issues. All of the fatalities have occurred on ascent, launch, ascent, and reentry and landing, because that's where the heavy energy transitions occur. You're converting chemical energy on launch to kinetic energy to get to orbit, and you're converting thermal energy on orbit to re-enter and land. And those high energy transition states are where fatalities occur. But the real risk, as far as duration goes, is on orbit. The longer you're up there, the more potential you have to have a problem. This is just a list of a very short list of all the things that have happened. We've had missions that were terminated because of medical issues, and these are listed on this row right here. A combustion event with carbon monoxide, a urinary tract infection in a male, and a cardiac arrhythmia. These are the three things that were in the process of being terminated or abort, returned to Earth, and when the system, the medical problem spontaneously resolved. We've had combustion events. That's a euphemism for fires on Salyut, Mir, shuttle, and space station. They're usually small avionics fires, but there were several on Mir that were very, very problematic. We've had events during spacewalks, including crew injury and mission terminations. And on the lunar surface, we had falls and musculoskeletal injuries. If you all want to follow this up further, I can show you that we've lost a number of tools on orbit, and the crew are highly trained. These tools are not your, standard tool you get at a hardware store. The tools themselves cost millions of dollars to make. And today we've had 43 events where tools and cameras were lost because of what we'll get into in a little bit later as a neurologic condition we call the space stupids, where your thinking processes are not as up to speed as you'd like. Pretty much every organ system has had some effect. And more importantly, the effects of a culmination of a lot of different things, including medical effects, but also sleep deprivation and maybe radiation effects on the brain, have resulted in performance errors. And performance errors are where you can kill yourself, especially when you have human in the loop systems. Things in space don't work the same as they do on Earth. We don't have sedimentation in microgravity. We don't have air fluid levels, and even something as simple as a flame actually burns it burns hotter and it burns more completely in space. So fires are a very interesting area that's being studied, because we know that if they happen, they're going to be very different than they do on Earth. For example, if you have a fire or smoke detector, where are the smoke detectors? They're put up high because convection will cause the hot elements to rise, and that's where you're going to detect smoke particles or whatnot. But in space, the fire does not propagate with convection. So huge numbers of things happen. This is a very simple slide that shows that every organ system in our body has a time course of adaptation to the microgravity environment, or the absence or alteration of gravity. And the nervous system reacts very quickly. Fluids react over days. cardiovascular system, and each one of these organ systems has a time constant for adaptation to the novel environment of weightlessness, and they have a recovery time constant that's quite different. For example, bone, which is one of those that is to date has never reached a stable endpoint. We think it's probably around 18 months that it's going to start to finally not lose bone based on spinal cord patients. But the time course of recovery is about 3 times as much. So if you lose X number of grams in say 6 to 12 months, it's going to take 3 times longer to recover that in the adaptation back to the gravity environment. This is a very broad schematic of all the different system problems that we face. And depending on your specialty of interest, you know, we can go into more detail on that, but suffice it to say that everything is affected. And the most significant issue is, does it have a performance concern? Radiation is the gift that keeps on giving. The solar particle events come off of what's called a coronal mass ejection, and they get thrown out from the sun, and that coronal mass can have profound effects on you. During solar max, there are more solar events, and these coronal mass ejections come out. They can cause disruptions in communication. And every 11 years, we reach solar max and solar min. And during solar max, there's a higher number of solar particle events. During solar min, there's higher galactic cosmic radiation. So we have these two competing forces, the galactic cosmic radiation, which is a lower level. It's unshieldable, at least to the extent we can imagine. And this is the one that causes chronic degenerative conditions that could affect crew after they return to Earth. The solar particle events are high enough that if they hit a crew during a certain phase of the mission, they can kill the crew or significantly affect their performance. Between Apollo 16 and 17, there was a solar particle event that happened that reached the lunar surface, that if we had crew there, there was likely that we would have had lost crew. That was just, they call it the golden BB. We dodged a bullet when that one happened. Now, the Earth's magnetic fields come out like a mushroom and go into the polar regions. And so at the apex or at the poles, the Earth's magnetic fields are shallower and closer to the Earth. And so there's less protection at the polar regions. And so when we have an orbit over the Earth, we see retinal flashes at the high latitudes, both south and at the south and north extremes. The space station is at 51.4 degrees inclination, and so it goes up really, that sine wave of the orbit is very high. It's going to be up much higher than this one. This was one of the Apollo missions, or Skylab missions, which was only, I think, 35, 40 degree inclination. There's also a hole in that electromagnetic field over the South Atlantic, and this is called the SAA, the South Atlantic Anomaly. And that's also an area where these retinal flashes from deep space occur. And the interesting thing is that's the same area that we see what are called computer or single event upsets. So just like those high energy particles that are coming in that cause retinal flashes, they also are hell on high density integrated circuits. So this is something that happens in the sphere of low Earth orbit at the extreme polar regions and also in the South Atlantic anomaly. So the point is, now in deep space, we're going to see more of those. And the Apollo crew talked about the solar particle retinal, or the retinal flashes that they experienced in space and some of the damages. Basically, it's, if you can imagine, if it can damage an integrated circuit, it can also damage neuronal circuits. And that's one of the deep concerns. Well, the consequence of deep space isolation is profound. This is Valerie Polyakov, a picture of him from Mir Space Station when one of the Soyuzes was coming up to meet him, and they actually took his picture, and he spent 5 hours a day exercising, and he spent the rest of the time looking at Earth. It was an endurance effort. He survived, he did fine, he had good muscle and cardiovascular function, but he kept himself from thinking about isolation because he could look at the Earth, and actually it was a pretty decent event for him. But what happens when the Earth is just the size of your thumb on the moon, or it's a barely visible pencil dot when you're on Mars? The neurobehavioral events that have happened in space would astonish you. Here's a list of them that I've compiled, and I've got these all referenced. It's unbelievable. We've had people that wanted to kill their crew member. We had people that after the various events, like in the Progress collision, one of the flight engineer wanted to kill himself, and I actually have video recordings of some of those situations. So we've had depression, homicidal and suicidal thoughts. We've had behavioral changes. We've had grief reactions. We've had fist fights, which would be pretty cool in microgravity because you're bouncing around like billiard balls. And we've had mutinies where the crew cut off communication with mission control. These are highly selected astronauts who are very mission focused, who've had significant behavioral anomalies. And that doesn't even get into the ones that have happened after flight. So there are things about space that can have some very detrimental effects. This is a photo of Jerry Leninger after the Mir fire. A solid fuel oxygen candle burned through its canister, and almost, from his description, it burned for quite a few minutes. And he said if it hadn't hit, the flame was coming off of it. And the solid fuel is self-sustaining. And if it hadn't hit a panel, if it had gone directly at the bulkhead, it would have ruptured the pressure vessel and they would have all perished. These are just some of the things that have happened. Carbon monoxide, ethylene glycol, nitrogen tetroxide. We've had heavy metals in the water, some serious environmental events. And then the ones I always like to talk about are the performance events. And there's a phenomenon that astronauts have described as the space stupids. Also, it's been called space fog, space viscosity or neuroviscosity, where the crew felt like their brain was like thinking in oatmeal. They felt like they weren't up to speed. We've had a lot of errors that have occurred, and we know from aviation experience that 75% of the errors are human factors related. But we've had missed checklist items that have resulted in significant mission events, lost tools, collision of a robotic arm, all kinds of different things. This is one I just used to show an example of. The crew worked on their spacesuit. They took the boots off and they put them on backwards. And, something as simple as if you've ever worn a tight boot when you've gone skiing or snowboarding, how uncomfortable that is. Imagine you're spending 6 or 8 hours with your boots on backwards. That would suck. This is a good example of, not having your stuff together. The big concern that we've discovered in low Earth orbit since 2005 is a phenomenon called it's now called spaceflight associated neuroocular syndrome, it was previously called visual impairment intracranial pressure. Now, the reason it happens is that absence of gravity causes all that fluid to come to your face. Imagine that you're in one of those inverted gravity boot things for back pain, and you're there 24/7. Look at Peggy Whitson, who's our long duration flyer. She's had 667 days in space. Here she is on Earth picture, and look at her in space. Her face is super puffy. Her eyes are like almost swollen shut, and that happened the whole time. That fluid shift is what we figure is accounting for this spaceflight associated neuroocular syndrome. It's caused evidence of higher increased pressure, including papilledema, buckling of the back of the eye called choroidal folds. the pressure on the back of the globe from the optic nerve sheath, which is swollen from the increased pressure, has caused distortion of the globe and has actually caused shifts of the our refractive index, so-called hyperopic shift. This is just a list of all the, it's about, if you look at all the different parameters that have been determined to be affected, it's about a quarter to a third of the crew have this phenomenon. This is in 6-month missions. We're very worried about this. I know I've got a lot to cover. So what's the chance of something bad happening? We base it on high performance crews, whether it's the Arctic Winter Rover, submarine, the astronaut longitudinal data, or military pilots, is the chance of a bad thing happening in 1 year to one person is about 6%. And by that I mean an ER visit or a hospitalization, something that's managed with a medium range of medical resources, and a high support requiring activity that would be, say, intensive care. A very substantial thing is about 2% per person per year. So you start figuring what's the likelihood in a 3-year mission for 5 or 6 crew members. And this is based on a 2.5-year mission with 4 crew members, based on the, the likelihood of an illness, injury, or environmental events. You can see that for that, something that would require a, an evacuation or mission termination, 1 in 6, for a serious evacuation, for emergent care, 1 in, less than 1 in 20. And for a loss of crew, it's in the 1 in 70 range. That's a pretty significant amount of risk. So when you go into this thing, you got to know, hey, there's a likelihood something bad's going to happen, and you need to be prepared for it, and also be prepared for the, the consequences. So a lot of what we do now is spend time on amplifying all of those 4 components. You have people, equipment, procedures, and training. And so a lot of the focus is on equipment, procedures, and training, including automated systems that can help out in a pinch. These are the drivers for any system, whether it's a medical device that we use on orbit. You'd like it to be small, lightweight, very durable. It could get wet. It could get stuff spilled on it. It could be dropped. It could operate in a mode that would be useful to a crew member, and it would be easy and intuitive to use. So these are things that are driving medical device systems for austere environments. And this is just an example of one of those that has been in the works for quite a few years, the ultrasound. In medicine, we have really heavily now started to exploit ultrasound because it is a less harmful kind of energy. You can still damage somebody with ultrasound, but it's not as bad as, say, X-rays from a CAT scan. And so ultrasound has been used since even the very early days of the space station. And this is a program, if any of you are interested in this, I can send you the links to it. We've heavily exploited ultrasound in space medicine. Now this thing requires near real-time communication. So it's this was done on the space station, and it was actually during the Columbia grounding of the shuttle. They said, well, what can we do? And they came up with this idea of using ultrasound and just training the crew with a short period of time, say literally 5 or 6 hours, to train them to do diagnostic quality ultrasound with real-time guidance. So this is a program called ATOM, and it basically breaks down all of the procedures on how you can do a diagnostic quality ultrasound with really a fairly minimal amount of training. And these protocols are developed so that and it's in a neat little booklet, and it talks about how you set up the ultrasound system and breaking down the keyboards into different areas, different anatomical locations, different orientations for the ultrasound probe, and how to do these various kinds of scans. And now they've come up with ability to scan pretty much every system, musculoskeletal system, ocular system, including the optic nerve sheath, the cardiac system. All these things now have been heavily exploited. This is Peggy, who is a renal physiologist, doing an ultrasound on her kid. This is a ureter squirt. So the ureter going from the kidney to the bladder, you can see the jet of the ureter going into her bladder. So the ultrasound has allowed us to heavily evaluate physiology in this microgravity environment. And these are just some of the publications. It was because this ocular system had already been developed that when they first recognized that this spaceflight associated neuroocular syndrome occurred, that they could actually start testing it. The ultrasound originally on the space station took up 2 huge rack panels. This was the ATL 1000. And probably 15 years ago, they came up with the laptop version, the GE VividQ, and now they're looking at the handheld V-scan or the butterfly system. So ultrasounds have obviously advanced immensely in this period. I'm going to skip through all this. It's in my handout so we can get to questions. Just on a big picture, we're heavily exploiting personal medicine or precision medicine in space to cover. So if you were in need of a drug, it would be tailored to you in advance by knowing your system. This is a fairly recent article just a few weeks ago on using omics from the twin study, looking at susceptibility to radiation, because that's a top driver, as well as sleep disruption, which is another concern, and also the spaceflight associated neuroocular syndrome. So for deep space mission, our crew health support plan includes this personalized approach, focusing on performance even above and beyond health, because performance can kill you with error. We want to have systems that can cover a broad range of capabilities and conditions. The downside to automated or semi-autonomous systems is the famous, computer that kills you. And it even dates back to the 2001 A Space Odyssey. And this is actually a scene from that, the HAL 9000. I'm sorry, Dave, I'm afraid I can't do that. So getting humans to Mars is going to require extensive amounts of planning. Using analogs like the wilderness medicine scenarios is a wonderful thing. Healthcare advances in precision personalized medicine is really a crucial thing, and as well as exploiting miniaturization technologies like ultrasound. So with that, I'll end. And sorry, I went a little over, but this was a very kind of a very cursory overview of humans supporting humans to Mars. This is a great quote from a self-trained Russian mathematician in the late 1800s named Konstantin Tsiolkovsky. He was a math teacher in a remote area of Russia. And he basically came up with the whole concept of orbital mechanics. These are from his notes from the late 1800s. And he recognized that there would be microgravity in space. So a lot of what we owe is to Konstantin Tsiolkovsky, who came up with this great quote, "The Earth is the cradle of mankind, but man cannot live in the cradle forever." So thank you very much for your attention, and hopefully we can get to a few questions. If not, we can always do this offline afterwards.
Awesome. Well, thank you so much, Dr. Clark. We really appreciate you you walking us through that. There was some really interesting information in there. I know Megan had a question for you, and I know a couple other folks had questions, so I'll kind of serve as a moderator for people who had to take off a little early. And to be respectful of everyone's time, this is recorded, so if you do need to leave for some reason, we are at that hour mark. And the last name, Gavin. So if you need to jump out or abort mission or whatever you want to call it, you can feel free to do that now. Megan, I'll get to your question first, and you have the floor.
Okay, well, hi, Dr. Clark. Thank you so much for talking with us today. I just had, I saw in your first slide that you are a board certified neurologist. And so I was wondering what led you to choose that specialty. And as M2s, we just finished our CNS module, so that's fresh on our brains, and how that has driven your career thus far.
You know, I've dabbled in a multitude of things, and I think neurology and neurosurgery attracted me just because I was always fascinated about how and why we do things and how we think through things. And so it was just one of those. Well, I originally started in marine biology, and my interest was in communication and in fish and marine mammals. And then I had a professor who, when I was in marine biology in undergrad, who said, "Hey, you got good enough grades. Why don't you consider medicine?" And so I just at the last minute switched over to medicine at the end of my college years. But I've always been interested in how we think and process things. And the brain is, a dolphin brain looks a lot like a human brain. It's got lots of gyri and the fact that there's all this specialization, and we're a unique species because so if you think about our heart pumps fluids and to provide metabolic substrate and oxygen, essentially fuel and oxidizer, and the brain makes up 2% of the body's mass, but it takes up 20%, 1/5 of the body's oxygen consumption. And you just kind of go, wow, I mean, that's a very, very unique feature for animals to have a small organ that takes up, 10 times its mass in energy. And it gives us the creativity. So that was just my, kind of my fascination with how we are as a species and how we think and do things. So that's my story. But it really started with how fish communicate, and then it led me to marine mammals.
Thank you.
All right, I know Gavin had a question for you as well, so I'll let the two last name sharers get after it. Gavin, you had a question?
Yeah. Hi, Dr. Clark. Thanks again. Hey. I really appreciate this.
Yeah, my pleasure.
It's also kind of fun to hear, the last name. I haven't gotten quite to the doctor part, but I'm here in my future. I was wondering, you're coming from a neuro background. I was sort of curious if you had any leading hypotheses on these like space stupids.
Yeah, I'll tell you that. So I had to, as a flight surgeon, especially when you recover the crew, as soon as they get back, they're just chatty Cathys, man. They'll tell you all kinds of stuff. And then the barriers of, we're really not invincible come back, or get covered up. But when they first come back, there would be, they would come to me and they'd say, I mean, it was weird, but I just felt like it's like things that your intuitiveness was lost. For example, you have all these procedures that you've trained to do. And it would be like, and this kind of dates the technology, but they would have like to put a cassette in to record some process, like they were mapping the Earth and they had to change the cassettes out, something real simple like that. And there would be a procedure on how to do it. And ordinarily you could just do it intuitively. I'm going to open my window so you can see better. But they would talk about how every little thing had to be spelled out. So something that when you go drive your car, you just instantly go through and you know what to do because you do it all the time. And then you're up in space and you're like, you lose they talk about losing their intuitiveness. And that's why procedures have to be written exactly, like ridiculously detailed, because somehow the intuitiveness gets lost. It's a dirty secret and everybody is trying to figure out what's really going on there. But the fact that astronauts would tell me, hey, this really perplexed me. And they weren't just the short duration astronauts, where you have this fluid shift and the fluid shift you know, is going to go away when they come back to Earth, but long duration astronauts would talk about it. So I don't know what it is. Now, I tell you what, if you really are interested in this, I'll send you a copy of my book chapter. It's in this book here called Principles of Clinical Medicine for Spaceflight. And it just came out. So I think it's either 2020 or 2019. And I wrote the chapter on neurologic concerns. And I go into a lot of detail on some of the really incredible things that people have, you know, from a neurologic standpoint. So this area is just, we're just scratching the surface on this. Is it, you know, I'm 67, so I can tell you that, man, I don't think as sharp as I used to. I still fly planes and everything, but I know I'm not as sharp as I was. So we've often thought of space and microgravity as a way to accelerate aging. We lose bone 10 times faster in space than we do on Earth. We have cardiovascular effects. You know, your heart loses its exercise capacity. It recovers coming back to Earth. But we sent John Glenn up to space to see what it was like. But space is a very good analog for aging. But what I wonder is it kind of like it's, you know, it's putting you, you know, into the future so you can see what it's going to be like, where you're, you know, you lose your muscle mass, you lose your cardiovascular aerobic capacity, you lose your intuitiveness. It's a fascinating area, but I can honestly say I have no idea what's going on. It could be fluid shifts. Now, the fluid shifts is a hot subject right now. And I don't know if you've heard this, but just recently, this fluid shift has been a significant enough concern that it's been documented that crew have had venous stasis in their cerebral vasculature, their venous vasculature in their brain, including one that was bad enough that they said, we don't know what's going on there, but there's a clot there. And so they put them on anticoagulants. So the fact that we are in head down tilt 24/7 for 6 months or, you know, longer is a real concern. And here's the thing that's really been intriguing. What we realize is that during sleep, our brain lymphatic system, the sewer of the brain, washing out all those metabolic byproducts, has got to work. And if you get sleep deprived or you somehow impair that system, you develop toxic metabolites that are associated with Alzheimer's, you know, the beta amyloid and tau protein, chronic traumatic encephalopathy that releases toxins that don't get washed out. So somehow I have a suspicion that sleep is involved in this. And sleep is not a passive process, it's an active process of memory consolidation during REM sleep. And deep sleep is when the brain is flushing out all the buildup of those toxic metabolic byproducts. And somehow in space, because of the venous congestion, the cerebral venous congestion, that metabolic process may be perturbed. So that is an area of huge effort right now to try to sort that out. Is that really a bad thing? But imagine if you couldn't drain the brain's sewer system like we're supposed to. They could have far-reaching consequences. Sleep disruption is considered a big problem in in aging and brain injury patients. If you get to deal with brain injury patients, a lot of them will talk about how they just can't sleep like they used to, or they're just always, upset. So I think that's the connection I somehow see of this, is this venous congestion that occurs with chronic, head down tilt that happens in spaceflight may have some very low grade detrimental effect to this, the brain's flush out of its toxic metabolic byproducts.
Very crazy. Thank you.
Awesome. Christine had a question that she asked in the chat as well. And thank you for that great response, Dr. Clark. I'll definitely chat with you after this to see about maybe looking into that book chapter that you wrote, because I've had some interested parties ask about that. Christine,
I have this whole book electronically.
Oh, wonderful. Perfect.
$400 book. Yeah.
Okay, very cool. Christine, you wrote a question in the chat. Did you want to ask yourself? I'm happy to. I guess you have to come off mute to tell me.
Sure. So with all of what you were just talking about, are we seeing like a lot of long-term detrimental health effects in astronauts even when they return to Earth, or not so much?
You know, I mean, there's a program called the Lifetime Surveillance of Astronaut Health, and it's been going on since the very early days. And they follow different conditions. You know, cancer has been a real concern with radiation, and the data on that is like, well, compared to the general population, the astronauts aren't any different. But if you compare them to, you know, high performing, healthy individuals, maybe there is a difference. We have a protocol that allows autopsies to be done. But very few people, we're not actively enough pursuing that, in my opinion. And we should be doing biomarkers on astronauts after they perish, you know, from natural or accidental causes, and look at some of these brain biomarkers, and also the, you know, the tau and beta amyloid, other things about that. It takes a lot of cognitive testing to really discern some of these deficits, and we don't do that. So we do a really good kind of cursory executive physical, but it doesn't get into the nitty-gritty of things that we're really concerned with. And to me, that's a real shortcoming, because by the time we finally come up to realizing this may be a problem, we may have another 20 or 30 years of spaceflight that's gone on. So in my estimation, we should be doing a more extensive surveillance program, particularly, you know, a neuro-directed autopsy. And I have colleagues of mine that do this, that have said, hey, we could do this, this, and this. At the very least, we take specimens and preserve them in adequate ways so that they could be tested in the future as advanced technologies and bioassays become available.
That's interesting. Thank you.
All right. I wanted to, and Christine, thank you for the great question. I just wanted to come off one more time to see if anybody else had any spontaneous questions. I know we had a couple email ones for Dr. Clark. So I'll take one of those. So Dr. Clark, somebody emailed prior to our meeting and asked us to ask you, what was your biggest, what was the biggest physiological challenge that you've seen in your career, or the one that surprised you the most? And have you been able to overcome that from a space medicine perspective?
So what physiologic challenge in the astronauts, or what is that?
Yeah, so I think they were writing in reference to like longer term space travel.
Well, I mean, obviously, you know, you see what you look for. And as a neurologist, my big fascination was always to try to evaluate the crew right after they came back, and get their perspective on things. Amazingly, what I realized is the human is a lot more resilient than we give them credit for. And I had seen, even in this would have been the early space station crew coming back, and they didn't have the advanced exercise countermeasures that we have today that give better resistive exercise and better aerobic exercise. I was shocked at how well people could do after long duration flights. Usually they were experienced. So if you send a rookie up to on a long duration mission, they generally are not going to do as well as somebody who's been in space before. Like, say, for example, there are some space station crews that hadn't flown in the shuttle before they flew to space station. But the early space station crews had all been shuttle experienced people. And I was just shocked at how well some of them would do tests, and I would do a really extensive neurologic exam on them. And it was like, you just came back from space and you seem like fantastic. And it's like, what is going on here? Because I've seen some that were, I mean, it was like they couldn't even recognize their arm. You know, you had to move it until, and when you finally moved it, they kind of recalibrated themselves. So to me, the thing that was fascinating was the diversity of adaptive and readaptive abilities that people had. Now, John Glenn was a good example. I kind of look at it like this. We have this ability in individuals to draw from experiences or whatever and adapt to a situation, and then this novel situation, whether it's microgravity or, you know, high altitude or whatever. And then there's the readaptation. Once you adapt to this unusual environment, like say microgravity, you have a readaptive time constant. In other words, and we know that the time constants of adaptation to the novel environment and readaptation to back to Earth terrestrial environment are different. And so John Glenn, he was 77 when he flew in the late 98 time frame. And man, he did great. He'd flown in space on the first orbital mission in 60, I think it was 62 or 3. And it was, you know, how many decades later he flies as a 77-year-old. And he adapted really well to space. I mean, unbelievable. I didn't have motion sickness. He was just spry. He was, you know, when he came back to Earth, we turned him into an 85, 90-year-old. He could hardly walk. He was like, you know, super unsteady. Now eventually recovered. So I came up with this idea that we have this adaptive reserve, and you kind of want to hold on to it until you really need it, and then use it as you need it. So he had a great ability to adapt to space. He'd been there before, but then when he came back, you know, we turned a guy that was physiologically, you know, a 50 or 60-year-old into an 80 or 90-year-old. In other words, we put him back into his chronological age as opposed to his, you know, very youthful age. So I've always been fascinated by this adaptive reserve that we have, and also that some people are better at it than others, and it may be domain centric. In other words, some people it's more affected in their cardiovascular domain or, you know, whatever. We had some people that had very little degradation in their bone mass. Ordinarily, they would lose 2 to 3%. Astronauts will lose 2 to 3% of their bone mass, bone mineral density, in 2 to 3% per month. And other people, they'd come back and they're like not even affected. So it's the individual, how our bodies and how we are uniquely capable of developing the ability to adapt to a novel environment, I think is a fascinating area. I think much of this is going to be hopefully elucidated with this precision medicine approach. The twin study was a great example of that, where Scott Kelly, you know, flew for 340 days, and his brother Mark, who was also an astronaut, was tested on the ground. Now, one of the things that's in the genetic analysis is that the idea is that telomere length is a benefit. It gives you some protection. And damned if Scott Kelly didn't come back with longer telomeres after his mission. I mean, that just blew everybody away. Like, what? They figured it would be shorter, and it was longer. So he obviously had a pretty good adaptive component, and his telomeres lengthened. Now, when he came back to Earth, they went back to his pre-baseline level. So my challenge to you all is, you've got this unbelievable opportunity for looking at people in novel environments and seeing how they adapt and readapt, whether it's in, wilderness medicine context or space or whatever. And so there's such a bright future for you all to try to figure this out now, because the tools, these precision medicine biomarker tools, are so much better able to. So there's a huge effort now in human performance and resilience. And it's not just something for high performance athletes, although they have heavily exploited this. You look at the high performance athletic community, they are always trying to figure out a way to eke out a better, cutting their time by a couple of milliseconds, or cutting their, or enhancing their endurance, or whether it's, whatever. But this domain is now open for the general public. So maybe there's things that we can better understand in how we deal with things by enhancing our resilience. And a big part of it, I think, because this is now something that's heavily being looked at in the sports and high performance world, is nutritional components. When and where to get this, that, and the other thing. Our microbiome, the intestinal bacteria in our intestinal flora, have more genetics. They have more genes than we have in our actual body. And so we very well, it may be something to do with what we eat and how we process it. And so there's a whole domain in the high performance resilience arena that's looking at how do we do the best by the biome component of it, the microbiome, which will have repercussions in other of the biome areas. So it's going to help protect us in radiation. It's going to help us understand better, better how we adapt to things that we change in our environment, whether it's higher carbon dioxide or, toxins in our environment or whatever. Anyway, I don't mean to ramble on, but I hope that answers your question.
Well, I know Dr. Sherman, who many of us have interacted with, he's our nutrition professor for us SMPs, would definitely appreciate the commentary on the gut microbiome, because we spent some very interesting time talking about that. So thank you very much for that well thought response. I know Stephanie had, I think, what is our final question for today. So no pressure, Stephanie, it's a great question. I'll let her have the floor and we will polish things off here.
Hello there. So Dr. Clark, earlier you had mentioned during your talk the psychological impact of prolonged isolation on these longer space missions that people have already gone on for the astronauts. Do you know if any research has been done into the effect of that type of separation with sort of uniquely limited communication for the family members who they're leaving on Earth? Particularly if you were trying to get into some of these longer, like 2.5 year and things like that, if they were going to Mars or something like that. I imagine there's proxies with like military deployments and whatnot, but.
Well, I mean, that's a great area. So to me, the big, obviously we have radiation. Radiation is a hazard, and then there's the consequences on different organ systems. And then there's the behavioral health is a huge component of it, because we have seen, if you look at that list, and I give this talk at NASA and I say, these are the kinds of things, these aren't things I'm making up. These are things that have happened in astronauts, and you look at them, you go, holy shit, are you kidding me? Wanting to kill the other guy, wanting to kill yourself, serious depression. And these are missions where you can look out and see the Earth. We've had we had an astronaut who killed himself after his space flight. There was a European astronaut who had a suicide attempt. Actually she was a colleague of mine, Lisa Nowak, who tried to take out a competitor's, this guy she was dating, she tried to take her competitor out. I mean, huge behavioral anomalies. So what's going to happen when the Earth is, when you go to space in low Earth orbit, the Earth is panoramic. When you go to the moon, it's the size of your thumb. It's this. When you go to Mars, it's a pencil dot, and you can't talk to somebody real time. it's going to have huge repercussions. So they're talking about having avatars, things that can react in a more personalized way. You know, it's interesting. COVID has started to realize we can do, you know, telehealth, telemental health visits. So we're going to have to come up with some novel ideas. But if I'll just give you a kind of a weird story I had heard, that the Mir crew members were not often well resupplied or provisioned. They were out to set records, and they ended up they found a roach in one of the resupplies, you know, food containers, and they adopted it as a pet. And I noticed Gavin had his dog there. You know, pets are really important. You know what else is really important? Seeing vegetables and fruit. The astronauts are so enlightened by, you know, because green is a very soothing wavelength to our system. So having plants and animals can be a huge psychological boost. You know, you look at The Martian, and you know, the fact that Watley would talk to the plants, and we would, you know, I mean, that you look at the Castaway, when Tom Hanks is talking to a soccer ball, even an inanimate looking, you know, anthropometric thing became his only friend. We're going to have to look at some really novel things when we're gone for years and years and years. And I can only come up with, you know, things that I consider concerns, but I have no idea how to solve these. It's going to require some really novel, you know, ideas, because the inability to communicate with somebody real time is going to be a huge game changer. The fact that you cannot see the Earth is going to be a huge game changer. That's what kept Valerie Polyakov sane, was just looking out the Earth. And his sleep station was I have a picture of it. His sleep station had nothing but pictures of his family all over the place. Now, one of the things that NASA does is they have all these pictures embedded in each person's individual computer that periodically pop up and just show a family scene, just to rekindle that connection. COVID has brought this to light, how much a hug is, just or physical, just even a fist bump, how important some of that is. So we're going to have to come up with some really interesting and novel ways to deal with the fact that we're physically and temporally separated on these long duration missions. We need pets, we need plants, we need, you know, things that make us human. And you all are going to find that out.
I just wanted to, speaking of human connection, I wanted to invite everyone to come off of mute if you would like to, and say a big thank you to Dr. Clark. I really enjoyed his talk today, I know, so thank you from me. Anybody else, you're more than welcome.
Thank you, Dr. Clark.
Thank you. My pleasure.
Thank you.
I'm officially passing the torch. Hey, you guys should get Yoder Vey to talk. He was a Georgetown med student. So he and I, and this was in the 80s or 70s, and he was at Georgetown, and he was an intern with me, but he trained at Georgetown, and he's one of the premier NASA flight surgeons. So you should get him to give you guys a talk, just so you can hear alumni.
We'll have to hope that can be an in-person talk in the near future, seeing how COVID.
Oh, he's a character. He's got
precipitating.
Stories. Yeah, he's got some great stories.
Well, thank you for yours, and thank you very much for your time. Everybody else, you are free to be dismissed. Dr. Clark.
Yeah, my pleasure.
You are more than welcome.
You guys have such a great career ahead of you. I'm convinced that, you know, one of you will walk on Mars someday. Maybe a bunch of you.
Me, hopefully. All right. Well, thank you, everybody. All
right.
Have a good rest of your break, Dr. Clark.
Yeah. Enjoy the holidays.
Thank you, and I'm glad you traveled safely home. We appreciate your time.
You bet. Thanks.
And Matt, if you want to stick on for a moment.